This video demonstrates the tasks, techniques, and apparatus used in our experimental comparison of perspective and geometry-based approaches to mouse cursor control in Spatial Augmented Reality, or SAR. Our SAR installation uses 3 projectors calibrated with Christie Mystique software. A 13-camera Vicon system tracks head and mouse pose. Unity Game Engine powers the system, which enables mouse tracking and placement of content in the real environment. For geometry-based cursor control, we introduce Everywhere Cursor, where the cursor follows the curvature of the environment geometry without relying on the user's perspective. The cursor is visualized using an orthogonal virtual projector. A set of short raycasts, called legs, orient and position the cursor, allowing the cursor to move around the environment like a bug. A raycast from the top left corner routes input events from mouse to UI components, making the cursor compatible with Unity's UI system. The cursor points upward on a vertical surface and forward from the perspective of the mouse on a horizontal surface, like on a desktop monitor. Using the legs, the cursor also stays parallel with the nearby surfaces. To detect the next cursor position, a circular raycast is performed with the radius equal to the movement distance. Because of the variable size of the circular raycast, the cursor can skip obstructive regions like gaps with a fast mouse movement to allow for faster interaction. We treat the monitor as a special case where the cursor jumps to the display when it enters the hidden region behind. The resulting cursor trajectory extends the interaction domain from planes to arbitrary surfaces, yielding a continuous and sensible movement path. Because the SAR environment can have gaps or unscanned areas that are too wide for the cursor to travel across, we implement a gap filling mode, which allows users to place virtual bridges across these regions using the mouse. Raycast clutching allows the user to reset the position of the cursor by tilting the mouse sideways. We compared Everywhere Cursor's geometry-based movement with perspective-based techniques, perspective cursor, and standard raycasting. Perspective cursor places the cursor onto the environment by rotating a raycast around the user's head. Raycasting projects a ray from the front of the mouse to find the cursor position. We conducted a controlled experiment of the technique in an office scene consisting of a desk and its surrounding environment, which includes a lamp sculpture made with a volleyball and a piece of cardboard representing curved surfaces, a monitor representing flat, user-facing surfaces, a bookshelf representing irregular surfaces, and a printer representing far oblique surfaces. Other objects create additional representative variations in surface geometry, including occlusion. The users performed selection tasks and tracing tasks using each of the techniques. The selection tasks are either short distance within one surface or long distance across multiple surfaces, requiring the cursor to take a longer path. In these tasks, we measure the selection time and error rate. The tracing tasks are either linear or circular. Here, we measure the tracing time, accuracy, and precision. For implementation details, see the accompanying paper.